Let's continue the afternoon session with Simon Baker, who's going to talk about something.
So, yeah, let me start with thanking the organizers for the opportunity to speak. I've really enjoyed the week so far. I've really enjoyed the interactive way the talks class, and I really want to encourage it in my talk. So I encourage questions, comments, anything. So what am I going to be talking about? Well, it's all about this one particular theorem, which is somehow the missing piece from Pavlov's talk in this analytic theorem. So this was a theorem proved by myself and Tuomas Sahlsten at the same time in Hong Kong. Federico Rodriguez and Jiren Wang. And this theorem is by an analytic IFS. Crucially, that is not conjugated to a subsimpler IFS. Then, well, then we get this good Fourier decay. Then every self-conformal measure as polynomial maybe I should also little disclaimer. So I know that a few people in the room were at in my lectures for the Technological Institute about a month ago, and very much the second part of this talk will coincide with what I'm going to go through today. Apologies for this. I won't take it personally. Choose to get a copy of it. Whatever. But what would be slightly different is, I guess the title of the talk was Spectral Gaps in Fourier Decay. And in this lecture at the Loughborough Institute, somehow I took the spectral gaps as a bit of a black box and then explained how from this you derive your Fourier decay statement. And what I'm going to do now is, in the briefest possible terms, how the non-conjugacy gives you a spectral gap. And this is a very challenging thing to do, so I'm only going to give you a bit of a flavour, but somehow it's a flavour hopefully you'll appreciate. So let's start by trying to get an idea about how we get a spectral gap. So there's a proposition which gets things rolling. So maybe throughout this talk, okay, I won't assume too much yet. So let's proposition. So phi A is not conjugated to a subsimilar IFS. So this is in the analytic family. So this is if and only if there exists two constants, C1 and C2 greater than 0, such that for all n sufficiently large, there exists two words in my alphabet such that if I look at this quantity which we've seen a few times, this is the derivative of log of the derivative of phi A prime minus log of phi B prime, derivative of that function. But what is the statement? It is that this is true for all x in Okay, so the upper bound, I don't think we've seen the upper bound so far, but the upper bound is just bound to distortion. The lower bound is the more meaningful state.
Well, it's only part you need the non-conjugated to a self-similar.
In the analytic family.
Only this part.
So the only part, yes, this is basically it. So from here on, I will be running assuming this condition. And in fact, what I'm about to say works in far lower regularity. It's just somehow this proposition. So yeah, you could think about what I'm actually going to prove is if you have this condition under C2, then you have a polynomial Fourier decay. So let me give this a name. So let me give it, well, I'm going to call this the uni condition, which is the unique one, which this condition was sort of going to install. Okay. So, great. So I've reinterpreted my conjugacy in terms of this my lack of conjugacy in terms of this uni condition. How am I going to use it to prove a spectral gap? So, a spectral gap, I need to think some operators. So, the operators I'm going to be interested in, well, these are going to be these twisted ones against where I like to talk. So, what do I do? So, I have S is some number in C, although actually, very soon I'll just sort of restrict the case where it's purely imaginary, so R will be 0. And then I define operator LS from the function 0, 1 to the cells. What does this look like? Going to be the usual transfer operator associated to the IFS, but then you have this twisting factor which comes from the derivative. Okay, so I have this this operator, and so the thing I need to define my spectrum because I need some suitable norm to define it. Another way to define it, so I have for B in R define the B norm on this space just to be the infinity norm. Well, it's used to define the function. So the B norm of a function, the space is going to just be the infinity norm plus infinity norm as derivative. The modulus. Okay, this particular choice of norm is going to be super important to us. Most of the time, there's not too much to be lost just thinking of the B norm as the infinity. So I have this operator, I have this norm. What's the important part? So this is again quite myself and Tuomas and our opportunity in some way is that you assume uni, maybe even a slightly weaker version, then there exists a row called 0, 1, such that for B sufficiently large, we're going to have so now we have a purely imaginary twisted operator here. And check this B norm is going to decay. So we get some, so the important part here is the row 0 to there. So yeah, that's giving us some good exponential decay. Okay. So a very difficult thing to do is to explain why this uni condition gives you this decay bound, but I'm going to try to give you a very loose idea as to why it works. So in the argument about it is going to be very hand-wavy, so again, I really encourage you to interrupt me and ask for the clarity. So let's try to outline, and this is really inspired by Dotto. It's by log object and node. In fact, the argument I'm going to give, it, and assuming that the iterated function system satisfies the strong separation condition, and then I'll explain how you overcome this issue shortly. Yeah, really, this is a strong separation condition. The proof of this is really due to node. What we do is somehow overcome the issue with overlaps. Okay, so let's just start off by thinking about this quantity. To say we're only really interested in infinity norms, so I'm really just going to address this term here. So the infinity component of this expression here, and I'm taking 2n. So the very obvious thing is that this is just the composition of this with itself. But what you do is, by an application of Cauchy-Schwarz, you can show that this is going to be less than L0 and sorry, I have to take some squares here so I can do Cauchy-Schwarz, but taking the square isn't an issue when you think about this infinity norm. So yeah, Cauchy-Schwarz lets you say this. Okay, so this is not too difficult, but the point is my twisted operator, I'm able to bound it above by an expression involving the twisted operator and the non-twisted operator. But then the thing I want to emphasize, thankfully Gaetan pointed this out, is that somehow when you have some function and you take your operator apply to this function, this gives you a very good idea of the integral of this expression with respect to the measure. Somehow, if you imagine, if you think what, okay, let me launch this now, and let's just think what it looks like. The n-fold composition unperturbed, sort of 0 here, is exactly this. Actually, I just have words of length n, and then my value is my function at this point. So each one of my cylinders has a point which belongs to it, and this weight associated to it. So really, I'm just sampling from each of my cylinders one particular point. So this is going to give you have to be careful on the regularity of this function, but ignoring that, this is going to give you a good approximation to the integral of this with respect to the invariant measure. So this is basically plus some negligible. So the thing you should take away from this is that A in the integral somehow applied by some K in the L2. So if I could show that this was going to be small, then that looks like this is. And the pretty useful thing is this is somehow this is independent of x. Sorry, this x here is what I'm integrating with respect to. So somehow I lost the x when I've gone from this step to this. So why should we expect decay in the L2 V norm? And this is where even the non-triviality comes into play. Let me just write out exactly what this is. So what are we integrating? We are integrating the A over A prime x e the fact you get this expression is just the decay. So what could give me some sort of decay? Well, this is this here is just a complex number. It's a complex number of unit length. So I basically see my original operator with this term. If I ignore this term, I have my original operator, but now I'm throwing in all these little complex numbers which are pointing in different directions. Okay. So what was going to give me decay? Well, we know if we have numbers in the complex plane, if they point in different directions, we see some cancellation in the modulus, right? We get some improvement on the trivial bound from the triangle inequality. Right, so somehow decay comes from these terms pointing in different directions. So I want these to point in different directions. So let's think about what this is going to look like for two different words. So ideally, if these are pointing in different directions, this means this won't be something close to 1, for instance. So this is exactly e to I b phi a b x, where phi is what we saw with Einstein's law. It is just this difference. Okay. So what's driving the different directions is this function here. Okay. So what would be an enemy to pointing different directions? Well, it would be if this was some kind of constant function, right? But what do I know? Well, I know. Okay, so I should say one more thing. If we differentiate this, phi a b prime is exactly maybe I need some more modular signs in here, but that's, oh no, actually, some point here, but essentially it is going to be this. I think there's something careful language to the modular signs, but let's ignore that. So the thing which is driving the change of this function is exactly what is over here in U. So this is telling me that the directions I see are going to change in a nice way as I vary my point x. Okay, and the fact that I have the C1 tells me there will be a change, and the C2 tells me it won't change too much. So how can you apply these ideas to get some Fourier decay? Well, what you do is you imagine you have your fractal set. You go down to some very, very deep level. And the level you choose is just a little bit silly this down here. The level you choose is informed by your choice of b, because b is also contributing to how this function changes. Right? Somehow I have it's not just by a bx, it's multiplied by this b as well. Just for this b is different from this b here. This b is a word, this b is this thing in the perturbation. Okay. So let's imagine in one of my cylinders down here, so this level is chosen carefully with b in mind. So maybe the gaps between successive intervals are of the order 1 over b. So imagine that I have a point in here which I get no cancellation. Okay, suppose I'm unlucky and the x I pick, these two terms point in the same direction. I have no cancellation. Then uni tells me that if I move in a very small way, which depends upon b, I go a little bit to the right. Here, I get cancellation. Here, I'm going to have things pointing in different directions. And I can apply this throughout, everywhere within the support of the measure. Right? Somehow I split my measure into lots of pieces which are size of order 1 over b. And then I just kind of travel across each one of my pieces, and I say, do I see cancellation or not? And the uniform uni condition tells me that you have to get some cancellation somewhere. And the size, the set of points where you get cancellation is going to be comparable to the size of the chunk of size y that we split it into. Okay, so what this tells you is that when you think about this expression, so maybe a useful way of thinking about this is that almost you're splitting you split your system into pieces. So maybe in each piece you get a bit of cancellation here, a bit of cancellation here, a bit of cancellation here. Okay. So from so some kind of point that you have to approximate this integral, where you would just look at those. You would split it into each one of these pieces. On those bits, you don't get cancellation. You take the trivial bound. You know, just imagine there was no cancellation. This was 1, and then those points where you do get cancellation, you exploit the cancellation. But there's one subtlety here, which is you need the measure of this region wherein you have cancellation to be comparable to the measure of this larger piece, right? Because it's no good if this would obviously true if I had something like the Loughborough measure, but it would be no good if you know the measure of this set of points which you have some cancellation is really negligible compared to the piece which you got to that resolution. But what is the standard way in which you can guarantee that the size of this is going to be comparable to the size of this larger piece? Well, this is where the strong separation condition comes in, right? We know this is struct, but if we have a strong separation condition for iterated function systems, we know that you know, if you have a ball, like you have a ball of comparable radius, and the measure of these objects will be the same, up to a multiplicative constant. Okay, so that's all you need, right? Somehow you go to the small scale, get little nuggets of cancellation, and you put it in here. Okay, now this is very hand wavy. There's a lot more to it, but hopefully you convince yourselves now why uni gives you at least cancellation here kind of regularly within the integral. Yeah.
Yeah. If you have overlaps, are the invariant measures still do big or not?
No, and that's the key
So
point.
that's the point.
Yeah, this is yeah. I'll say I'll address this more directly in a moment, but well, short answer is so are there any questions about what I've said so far? Okay, so all right, so this is a bit of an idea of how you get this condition gives you spectral gap. Let me say a little bit about this issue Gaetan raised, which is what we kind of handling these tables here, which is somehow how do you overcome the issue of overlaps, because it's entirely possible you're not doubling, and it's entirely possible that this nugget you pick, this very small measure relative to this larger set you've it's contained in. So it's best really do this with an example. So let's suppose my IFS was consisted of 4 maps. Okay, and this IFS is overlapping, so the measures could well not be doubling, the stationary measures you get here, the subconformal measures. But let's suppose it's true, but crucially, that phi1 and phi2 as an IFS, and phi3 and phi4 as an IFS satisfy the strong separation condition. Okay. So this is not really much of the restriction. You know, if you imagine about your iterated function system, you should expect to be able to iterate it to some level and find pieces which satisfy the strong separation condition. Now, what I'm going to do is I'm going to use this partition to split up this sum with with this term back here. And this is best illustrated with a picture. And so if we imagine the branching tree corresponding to this. So I have 4 choices of first map, and then I branch a bit further. I have 1, 2, 3, 4, 2, 3, 4, 2, 3, 4. So I have I have 16 words corresponding to all the different paths I can take, but I'm going to collect words using this partition. So I'm going to collect words based upon the partition elements they see at particular levels. So I'm going to collect words if the first digits. Okay, this is maybe best similar example. So I'm going to collect. So one of my partition elements would be phi1 composed with phi3, phi1 composed with phi4, phi2 composed with phi3, and phi2 composed with phi4. So somehow my first entries belong to this sub-IFS, and my second entries belong to this IFS. Okay? And you can see how this could give me a more general partition at any level. I just collect those terms such that the first level they belong to this sub-IFS, the second level they belong to this sub-IFS, and so on. Okay? And you can think of this as somehow I collect these two together, then maybe I collect these two terms together, these two terms together, and so on. Okay? So this partition is giving me a rule by which I'm going to partition this set of words. Okay? And this is really useful because this collection here is going to look like an iterated function system which satisfies the strong separation condition. Even though there's not an invariant set, there's no overlaps. Okay? So this means you don't have an invariant measure in this case, but so somehow you might think, well, how am I going to study an expression like this where I have a mu? That actually isn't that much of an issue. The lack of a stationary measure isn't particularly important because you can imagine this step when you go from here to here. Well, your mu just needs to be some measure which is going to give mass. So if you think about the strongly separated case, your mu just needs to be some measure which gives mass PA to the cylinder corresponding to the word A. Then you have this statement.
So you're getting a kind of a Q product system where you're taking the IFS at every step that is separating it, and you're collecting the dynamics of that SSC.
Mm-hmm. Yes.
Okay.
So somehow I collect words according to this, and that means that when I would sum over this, so I would sum this expression for this. What I'm really going to do is I'm going to sum over somehow partitions of A and N given by my initial partition of the IFS. But this initial partition is going to inform a partition on all words of length n, right? And then I'm just going to, so this is summing over the partition elements, and I look over the A in that particular partition element, in partition element.
In POGMF.
Yeah, something very big. So the point is this object here, so this would have the same, PA by A prime X, I B N by X. This looks like a transfer, well, this looks like a transfer operator for a well-separated iterated function system. Okay? It looks like it. In reality, what it is it's a random composition of transfer operators coming from a individual. It's a random composition of transfer operators, each one of which corresponds to a well-separated iterated function system. And the point is somehow you take this idea and then you plug it into this original dog with cat and home machinery, and you can prove spectral gap for these. There's one little careful thing you have to do, which is make sure that, I've partitioned my IFS. I have to make sure that I partition it in a clever way so that I not only satisfy the strong separation condition, but also so that I don't do something silly which kind of throws away the unique condition thing. I want my unique condition still somehow to be prevalent in these random partition elements I'm getting here. Okay. So this is a very, not too handwavy explanation how you go from uni to spectral gap, and then how you overcome issues with overlaps. Okay. But are there any questions about that?
Are you doing this then in expectation, or like first moment things that when you're looking at this, or how do you decide which partitions you're actually choosing?
So,
I mean, I get the idea of this, but I'm not quite seeing how you.
you can actually be so what you can do is you can partition it in such a way that, so I can partition it such that phi 1 and phi 2 and phi 3 and phi 4 will, so this IFS and this IFS will both satisfy unique. So somehow I don't really need to worry about somehow maybe I have an IFS which has some uni and one which doesn't. They're all contributing.
And then for all of the sequences of compositions of IFS, you still have
more or less.
Okay.
So for any IFS, you can iterate the level of a group into sub-IFSs.
So you can, so yes, basically you can take any IFS, you go to some deep level, and you can partition it into finitely many sub-IFSs, each one of which on its own would satisfy union.
And a strong separation.
And strong separation. Yes, there's a little more you have to be careful of. It's somehow, but yeah, we don't want to get into these technical ideas, but this is the idea. I'm partitioning it in exactly the way I'm just having a strong separation condition, and I get uni. I have now a random transfer operator instead of a single one, which is the problem that I don't really have any variant measure anymore, but I have a strong separation condition. Right. Are there any questions about that before I continue? No. Okay. See how I think. Not too bad. Okay, so now we're really on the second part, which is this using spectral gap to get Fourier. So the second part is spectral gap implies Fourier. So now see a few things which were seen before Emma was talking about. I'll introduce a definition which might sound a little strange and first down, but I'll say a bit more in a moment. So I'm going to say that mu is uniformly, so mu is going to be measured in R, but well, now mu is measured in R, I say it is uniformly and finally non-concentrated. If there exists C greater than 1 and delta from 0 infinity to infinity, such that delta goes to 0 as what you're evaluating goes to 0. And I have this property that for all x in the support of my measure, for all R being 0 and 1, and y in R, I have that the measure of my ball of x of radius R intersected with the ball centered at y at radius epsilon r, this is going to be less than or equal to delta epsilon, that's the measure. Okay, so you might think, well, there's nothing affine about this, there's no affine subspaces. So this is because it has this very straightforward generalization to higher dimensions, where instead of taking a ball of a point y, you take a neighborhood of a hyperplane. Okay, and I'm having this higher dimensional terminology for this one-dimensional object. I hope you'll forgive me of this. But let's really think about what this is saying. It's saying you have the measure of your ball, and you say, okay, within this ball, how much of the mass of this ball is allocated within this smaller ball? And you're saying that you're getting some genuinely quantitative decay in terms of the radius of the smaller ball. Okay, so it's saying that, in other words, the measure of your ball, you have some large ball with some radius r. The measure of this ball cannot be concentrated in a ball of much smaller radius than itself.
On the right side, you can see R.
Thank you, absolutely. So this is an important point for us yesterday. My C here didn't appear, and it's important that you would have this here. And then crucially, when you have this C, this condition is satisfied by all self-similar measures, all monatomic self-similar measures in R, and all non-affinely reducible self-similar measures in high dimensions. And if you certainly going to be satisfied in lower dimensions by all self-conformal measures in R. So we should think to ourselves, this is going to be a condition which is going to hold very, for all the self-similar measures we're interested in. Okay.
And yeah, just to come to the C, it is needed to do that.
Yes. Yeah. If you have a strong separation condition, or maybe a strong separation condition, C could be 1 here, but we need this fails if you take C equals 1 for some overlap. Even under the open set condition, this fails with C equals 1 for subsequent measures. You need a C here for to overcome issues with overlaps. But anyway, we have these measures. We have this property which says if you have a measure of a ball, it cannot be concentrated in a much smaller ball. And if you have this, then there is a theorem due to Osama Khalil, which Alan alluded to earlier, which is that if so this has a straightforward generalization to higher dimensions, so that's why I formulated it this way. So if mu is if mu is uniformly affinely non-concentrated, then for any epsilon greater than 0, there exists a tau greater than 0 depending on epsilon, the non-concentration parameters, which are the delta and C in this definition here. Remember, the function delta is what describes the decay, and we're going to see here as well. Such that the set of frequencies in when using T instead of R, there's the set of frequencies for which I don't decay by T to the minus tau can be covered by big epsilon, T to the epsilon, many balls of radius 1. Okay. So somehow this is telling you if you're uniformly affinely non-concentrated, the set of frequencies for which you don't have polynomial Fourier decay is a 0-dimensional set. Because I'm covering it by T to the epsilon many balls of radius 1. This is very much dimension 0. And I want to emphasize that the implicit constants in here the implicit constants and the upon epsilon is the notation indicates the non-concentration parameters and the diameter of the support. Although this final condition isn't, we don't have to worry about this too much. The really important thing is somehow that the thing I really want you to take away from this is that if you have a family of measures, all of which have the same non-concentration parameters, okay, so I'm about to say it's not technically correct, but this is what I want you to think. If I have a family of measures, all of which have the same non-concentration parameters, then for any epsilon, I can pick a tau such that this statement works for all of these measures simultaneously. This will be something which I will need in the proof of the statement which was up here. This is slightly different to what Amman had. I have slightly more technical dependencies, but yes, this will be important to us. Okay, so this is this nice theorem of Khalil, which gives us Fourier decay on average, Fourier decay outside of a zero-dimensional set.
So I guess the point being that in my case, when we have some sort of measure, everything we scale back from the same measures, we just simplify this with one measure, whereas when you have some full measures, or it's look slightly.
Yeah, you're jumping to the proof, but exactly, there's a point in the argument where so I will somehow take things to a small scale and then blow them up. Now, when Amman does this, he takes a small self-similar measure and he blows it up in some affine way. This is still basically a self-similar measure.
Yeah.
But what I'm going to do is I'm going to take a non-linear image and then blow that up in an affine way. Okay, I'm not doing the inverse of my nonlinear contraction. So this means that the blow-up measures I'm going to get are potentially going to be very different, but they will all have the same non-concentration parameters. So I'll be able to apply this same to all these measures uniform. But this will come. I'm getting a bit ahead of myself. Okay, so right. So now I'm going to assume I'm going to have my IFS. I'm always assuming I have this unique condition, but now I'm going to also assume I have a strong separation condition. And I'll explain how this issue is overcome later. So let's assume the strong separation condition from here on. Let's take some frequency psi, and I'm going to want to, this is a frequency I want to prove some, get some bound on its Fourier coefficient, and to it I'm going to associate a set A psi, which is in Amman's language, it's some suitable stopping time. So this is going to be those finite words. So this is finite words such that the derivative is going to be, let's say, comparable to psi to the minus 2/3. This is giving me, so okay, this is a really nice thing. Let's say I do, it's less than or equal to this, and then if I have in, now it's a genuine stopping time. So what do I mean here? I take my finite words such that if I take the infinity norm of the derivative of that word, it decays like this. But if I were to throw away the last digit, which is what A minus means, if I throw away the last digit, then my infinity norm is slightly larger than this. Okay, this is a very, way I don't particularly like way of saying that somehow I'm capturing words, all of which decay like psi to the minus 2/3, and I want to do it in such a way that I'm not going to have one word being a suffix or prefix of another appearing.
So I had a 1.5 in my talk. I guess the point is that is the similar to that. So
I was asking myself this, but yeah, maybe this is exactly the yeah.
You can choose something between half and one, and you do 5, right?
Yes. Yeah. stuff. Okay, so I have this cutoff set, and I need to introduce a little more notation, which is that for A in a finite word, I let XA be the unique fixed point. So this is somehow where X omega in Amman's talk, so by A and XA same. And I'm going to introduce a measure associated with the word A as well. So I'm going to let mu A be the restriction to the cylinder corresponding to that word. So here, X is the support of my measure, it's my self-conformal set. So this is just, mu A is just the measure restricted to this particular cylinder set. Okay, and because there's no overlaps, this is going to be precisely the push forward of my measure mu under phi A rescale. So this is an object which exists at scale psi to the minus 2/3, but it's far more useful to think of it blown up to be at scale 1. So how do I do this? I let mu A psi equal what I get when I push it forward by psi to the 2/3 mu. Okay. So what is this map here? This is just a map which scales X to Rx. So I have my measure which exists on my cylinder, which is a roughly diameter equal to this. I blow it up to be order 1 just by pushing forward under psi to the 2/3. Okay. So I have a lot of technical stuff, but this very useful position now, which says if I have some psi in R and n psi is equal to the integer part of log psi for some c greater than 0 small, then the rate comes from this particular frequency, they can bound it above the following way. Taking the sum over A psi EA, and then I have if I go into this corner, now we'll be able to read it. So let me just write this again. So my sum over B in A psi E B, I sum over A in A N psi. So this length, I have EA, and then I have the Fourier transform, not of mu, but of V psi by A prime X B psi divided by psi 2. Okay. So this. So okay. So that my single frequency I'm interested in, I'm bound to get above by an expression involving first of all many different measures. Somehow each one of my B's in my cutoff set is contributing to a measure in here. But the really important thing is that potentially we're seeing different frequencies here. Each word A, this summation, is potentially giving me another frequency, right? So why is this useful? So if we think about this Khalil statement, it tells us that our measure, for most of the frequencies we're going to pick, we're going to get Fourier decay, right? Outside of the 0-dimensional set. Now this is absolutely no good if I want to apply it to a particular choice of psi, because maybe the psi I picked was one for which I didn't have Fourier decay. But what this is doing is this is an expression involving potentially many different frequencies. Right? So if I could show that this set in here was a positive dimensional set then I could apply this in a meaningful way. Because I could say it's positive dimensional. Most of these frequencies has to give me polynomial Fourier decay. Sum it all up, do some averaging. This will give you Fourier decay of this particular frequency. So this is the strategy. I want to prove that these frequencies will satisfy some suitable non-concentration, and then I can apply Khalil's theorem in a very meaningful way. And this is what the spectral gap allows us to do. Okay. A little proof this. Okay, I'll say something very idyllic proof. So, no, this, nothing particularly fancy yet, but you can apply self-similarity to say that this is in fact the sum of A in A n psi PA to the 2 pi I psi I A x. And then what we do is something very similar to what Alan did. We approximate. Well, actually, first of all, we split our external integral into pieces which are informed by this word B. And then we take a first order approximation to that local within B. Okay? Somehow, first thing is that if I want to approximate this by its derivative, then, well, it causes too big an error because you're taking an integral over the whole domain. But if you go to some small scale, so in particular, if I sum over B in a psi, and I take the integral, and I focus on the particular cylinder corresponding to this unit B, so I take phi B x, and then I write this expression. When I look at this expression, then my first order approximation to this given by the derivative at this particular point xb, which is a particular point in here, this is a good enough approximation. Okay, your first order approximation, because you're looking at a small scale, is now okay. So morally, what this allows us to do is to, okay, you take your first order approximation. If you take your first order approximation at xb, and maybe you take the modulus. Okay, maybe I keep this modulus outside for now, and that will give you this. Okay. So now the question is, where does this mu b psi measure come from? Right. Somehow this expression in here now is an integral with respect to mu. How am I able to integrate with this mu b psi? But it's really just remembering what it is exactly. Mu b psi is the restriction of mu to the cylinder set. So somehow that's already appearing here because I'm restricting my integral to the cylinder set. But how do I go from mu b psi is this measure blown up? So how do I get the blow up? Well, I just take a factor of psi to the 2/3 out of psi, and that will give me my blow up. And what do you know? In this expression here, it's not psi, it's psi divided by psi to the 2/3. So this is what gives me my blow up. So actually, you happy?
Yeah. Yeah.
Okay. And what do we think? Is this clear or do we like some more?
So you have a strong separate condition making a restriction to custom it back.
Yes. So here it's very. For me, it's very. So this is where the strong separation condition is used to get this statement here. What are we happy with? Okay, well, I'm more than happy to spend some more time explaining this strong. But okay, maybe we ignore the proof and we just think to ourselves, we have a single frequency. Now we've got an average involving many frequencies. Maybe we can apply Khalil's theorem in a meaningful way. And that's exactly what we're going to do. there's one technical point we have to address before that. Maybe I'll just say this technical point and I won't write it up, which is that in this expression here, I have many different measures. I have all these different mu b psi's, right? So maybe Khalil's theorem would work differently for all these different b psi's, right? They all, it's just a statement, it's just a statement saying you have some Fourier decay on average, but maybe the scales of which would observe this Fourier decay on average would be wildly different for the different b's here. But thankfully, this is not the case. I can find some non-concentration parameters, some delta and some c, such that for any b and psi, this would hold. So my uniform non-concentration parameters can be chosen independently of my mu b psi measures. So this is great, because this means I can apply Khalil's theorem in a uniform way to all these measures simultaneously. Okay. And this is a technical point, but a very, very important one to know. And the proof of this is not too complicated, because really you're just taking a small piece of your measure and you're blowing it up. And if we think about our, the self-performable measure we started off with, which satisfied the strong separation condition, it's very easy to verify that this single measure would satisfy this non-concentration property. It's just your original measure, and somehow all these mu b psi's are somehow built using this original measure. So somehow all the calculations which you would do to verify non-concentration for one of these, you rephrase in terms of a calculation involving mu, and that's why you get this uniform statement. Okay. So now this is the kind of the missing ingredient in our decay statement, which is that there exists some gamma greater than 0, such that for any the natural numbers satisfy. This is a technical restriction I don't want to think about too much. Laying in this regime, so you should really think of okay, so we should think of these frequencies here are all going to be lying in this range. Okay? Maybe I can ensure that I don't contract too much here, such that my frequencies always lie within this range. So somehow the end here is going to capture one of these, quantify one of these bad intervals that appears in Khalil's theorem. Okay. Such that for any n in here and b in a psi, we have the non-concentration statement. I sum over a psi, b. I ask myself, how many of these lie in this interval? And this is bigger of side minus. This is the non-concentration. So this is telling me, imagine you had one of these bad integers which you didn't have Fourier decay. How many of the frequencies appearing in this expression are going to be unfortunate enough to fall into this interval? This tells you that it's going to be a small set. So I look at the measure of those which do exactly that. And what do you know? This decays polynomial inside. So something which is quite instructive to think of here is that this statement is absolutely not true if your IFS is self-similar. Because there, as analytic multiplication is commutative, So you see very few expressions here. So there will be one choice of n at least, which will have maybe just a logarithmic path here. But I've always used to prove upon the logarithmic path.
You mean like homogeneous case?
Homogeneous, absolutely. But homogeneous is super clear, right? Because somehow that's just going to be a single term in here. So all of there will be an n for which this maximum will be 1. But even in an inhomogeneous case, you can't build many different choices of derivative, again, because of mutativity.
Oh, okay, since they have only polynomial choice.
Exactly. So now here, basically you have exponential choices for this. And yeah, it's slightly confusing, but it's because I take a log side here. That's why we just see polynomial here, but really because it's a log side, it's like an exponential. So this is basically what you need to prove the Fourier decay statement, right? Because somehow now what you will do is you'll take this expression and you split your sum up into certain pieces. You would split it into those which you had Fourier decay, and you'd say, well, great, I've got polynomial Fourier decay, I don't need to do anything with this. And you said, okay, well, what about the contribution to this sum from those terms which don't give me Fourier decay? I want the contribution of precisely this summed over all the different bad ends. Now, I know I have very few bad ends, right? This is what Khalil's theorem told me. It told me I have polynomially small, a dimension 0 set of ends for which I need to consider this term. So there's nothing really to be lost by just imagine there's just one bad end. But I can see the contribution to this summation coming from this one bad end. It's a polynomial decaying sign. So that's everything you need now to get to the full polynomial Fourier decay statement. I'm squeezing that argument into this. I'm a little one eye on the time. But if you want further explanation of this, I'm more than happy to make time later. But what I want to do now is explain how do you get this statement from the spectral gap. Right, this is the one point where we're going to use the spectral gap. So let's do this. So the first thing I want to do is I want to reinterpret this long subinterval in terms of a condition just involving the word a, and this is easy enough. So we observe that phi a prime xb psi divided by psi 2/3 is going to be contained in some interval is equivalent to log of phi a prime xb being contained in some interval, which is going to be log n divided by psi to the 1/3 log n plus 1. This interval I n psi. So my non-concentration now is just rephrased slightly, and looking at those a for which log phi a prime xb is going to belong to this interval here. So I'm just bounding, so this summation here is now bounding, so looking at this event, I'm now looking at this event. Okay. But what's useful is I'm going to approximate this indicator function, the indicator function on this interval with some smooth function. So we choose a smooth summation to the characteristic on this interval, call it hn psi, and it satisfies obvious condition you want it to bound this from above. And you want to have a little bit of information on the norms of this as well. So the L the L1 norm of this is polynomially inside. You should think that the size of this interval, it's not obvious, but the size of this interval is roughly polynomially small inside. So this isn't much of a condition here, but I also want the second derivative to be too large inside. Okay, so this is some polynomial growth, but it's some arbitrarily small choice of eta. Okay. Somehow, if you imagine, if you have some, if you have the indicator function of some interval, if you want to get a good approximation to it in terms of its L1 norm, then you have something which looks like this. But this comes at a cost, and the cost is that the second derivative is going to have very large L1 norm. Okay, and in fact, you're always going to see a relation like this. Somehow we go from a side to some negative power to some side with some positive power. But what I can do is I can say, well, I have my small interval of size minus delta, some small delta. I'm going to take an approximation on some interval here, which is maybe of size minus eta, where eta is very small. But this is, so you can always do this. Your eta could be arbitrarily small. The important thing is there's some, for any eta arbitrarily small, this is going to be true. So now let's think about this expression, the thing we want to get to the upper bound for. And maybe you announce it, we'll see the magic where the transfer operator will appear for a bound of this expression. So the first thing to observe is that some EA chi I n psi log I a prime. This is bounded above this relation. This is bounded above by h and psi evaluated at the same thing. Okay. So fairly modest so far. But then what I do is, because h is smooth, I can use Fourier inversion formula. So now this is bounded above by the Fourier transform of psi. No, definitely don't want a psi here. I want maybe a parameter. Omega. Okay, let's put omega in here. We'll see what we do. And then I have e to the minus 2 pi I omega log I a prime. Okay, so it's just for inversion formula. But the thing you should notice is that I can bring, so this summation was over A in A n. So I can bring this summation and put it exactly there. But this is the same integral h n psi hat omega sum A in A psi P A e to the minus 2 I omega log x b. And we'll point to this. This is exactly the transfer operator by a certain number of times against a particular potential. This is exactly, that's applied to constant function 1. So this is exactly transfer operator applied again, psi times with 2 pi I omega I to the function 1 evaluation xb So now we can use the spectral gap, and somehow I can look at the infinity norm of this. Okay, and basically I am aware these arguments are quite complicated, but the point is basically from you. I'll do the argument, but you basically put in your spectral gap bound here, and you'll pull out a term like this. There's nothing really fancy anymore from this point onwards. You use Fourier inversion, it allows you to reinterpret what you want to bound from above as an expression involving the twisted transfer operation. Okay. Now, for those of you who remember the state of the spectral gap result, wasn't that for all twisted transfer operators you had some spectral gap? It was that for all b sufficiently large you had a spectral gap. This has to be true because if you have b equals 0, you get no spectral gap. So I have to be a bit careful, and I have to split this integral into 2 pieces. So I maybe take my omega in some small region governed by some parameter theta, and I ask myself, what would I get in this case? Well, in that case, I just take the bound from this expression coming from the norm of this, and I can bound this above by its L1 norm. And that is exactly what I have this here. Yeah. So the bound from the small frequencies, I just get this is bounded above by the L1 norm of this, which decays like psi to the minus 8. Okay. So small frequencies take a trivial bound, easy. But then there's large frequencies, which I have a spectral gap. I am bound this above, maybe I take its modulus, and then to take the modulus of this, and we get my rho 0 and psi, and I would have maybe omega to the notice this is the spectral gap statement, but I don't actually have this. So when I formulated the spectral gap statement, the side which had the bound had this rho 0 raised to some power, this parameter b raised to the parameter power 1/2, but it also had something involving the b norm of f. But my f is just a constant function 1. So its b norm is 1. So it's there, but it's 1. Okay? So the key thing to notice is that this is of the right order. So if I take this out, I get rho 0 to the n psi. Now, n psi was some c log psi. So you take this out, this is really giving you some polynomial decay in psi. So this is like some psi to the minus some very small delta, and then I have left with the remaining terms hn by omega omega above omega. Okay. Now my function h here was some very super function. So I can use integration by parts to get good bounds for this. So this is something that I also mentions very briefly, but basically integration by parts implies that this is always going to be bounded above by expression involving the L1 norm plus an expression involving the L1 norm of the second derivative. This is just integration by parts. So if I plug this in, what do we see which is good? We see a w to the half divided by a 1 plus w squared. So that's telling us our integral is going to be finite. The problem comes from maybe these norm terms are going to fight back in some meaningful way. But the L1 norm of h, well, that was always decaying. the L1 norm of the second derivative, it was growing, but the eta could be made arbitrarily small. Right? So what does this mean? The bound you get from this expression, from these considerations, is this should be bound above by psi minus delta. I would have an integral into the half 1 plus w square. Maybe I didn't have a. Oh, I did have to. And then I would have these terms coming from the norms. Now these can be taken outside of my integral, but the only term that really I have to worry about is this, the L1 norm of the second derivative fighting back against me, and it fights back like this. But it fights back in a negligible way. So this is psi to the delta plus eta, and eta is arbitrarily small. So this gives you a. So the way I maybe would prefer you to think it is somehow you start about asking about this event, you reinterpret it in terms of something just involving log of the first derivative, and yes, you think about this being evaluation of some indicator functions, and then you take some smooth approximation to indicator function. Fourier inversion, you run it through, and then you see the transfer operator. Okay, and basically, this kind of technical stuff here, but I think it's for our purposes sufficient to think that the transfer operator is going to say just basically give you exactly the right decay you want. Right, so we get this p rho 0 n of the psi appearing. That's exactly the thing you need. The rest is just some kind of bit of technical busy work. Okay. Right. So let me just say one final thing, which is okay. So this is under the strong separation condition. How do we yes, we needed the strong separation condition when we did this approximation argument, where somehow we thought about our Fourier transform bounded above by some average involving the first derivatives. So how do we overcome this? How do we overcome this issue? Well, basically, we're going to apply the same idea we saw previously, which was you take your big IFS and you partition it into sub-IFSs, each of which are well separated. We're going to do the same thing. And this is going to allow us to disintegrate our measure mu in terms of a family of random measures. Now, each one of these random measures, it's not a self-conformal measure, but it kind of looks like one. And in particular, it will satisfy, so it will have some dynamical invariance which comes from the transfer operator. And crucially, it will also look like a self-conformal measure. So when I would do this approximation argument, where I would say, yes, I go to some, I have some stopping time. I pick a cylinder corresponding to that stopping time. I look at pick a point within it. Think about the first order approximation coming from this point, and introducing these measures in UB psi. When I would do that with these mu omegas, the picture would be exactly the same because I have this good separation properties. So somehow to get the statement in full generality with which allow for overlaps, you just would need to prove that each one of these mu omegas has some polynomial Fourier decay. And yeah, so basically you have to take this argument here, but do a random version of it. And that's certainly achievable. And that's how the argument goes. Maybe that is that. So this this final part of the argument, which uses this idea, this doesn't appear anywhere. This the arguments we originally give. This is Tuomas and I uses this complicated sum product result of Organ and his adaptation of an argument due to Tuomas and his former PhD student Conrad Stevens, and this argument doesn't really need to worry about overlaps in this. Okay, right. Thank you.
Great. Questions?
How could you make the choice of the probability with high probability, the random part?
So what?
I mean, if divided the two product lines are separated apart, unless it's a error, so sure the error is small enough.
I'm sorry, can you say that?
You divided the sum of the two product lines have separated and other is have errors. How do you make sure the error is small enough?
Oh, this comes from well, it's exactly kind of the approximation that Alan alluded to. You have your so phi a of x is going to be very well approximated by so within for x in phi b of x, this is going to be phi a prime x b x minus x b plus some big O x minus x b squared. Now this, taking this 1.5, this minus 2 over 3, this is going to be like psi of the minus 4 over 3. So in terms of when you put this in the exponential, this would have a sign pointing back against it because this is your frequency, but it's still going to be some decay. It's going to be a psi to the minus 1/3. So this is why it works.
Other questions?
So the strong separation condition based on this argument basically your paper is Osama and one-dimensional.
Yes, so the argument I gave is the one-dimensional version of this.
Okay, and in the overlapping case, it's like the same thing, then you add the this stuff to substitute.
Yes, so this is as I said, this hasn't formally appeared anywhere.
Yeah.
But somehow there's kind of two routes you could take. You could either use the spectral gap in a meaningful way or get in some product world which are quite exotic and slightly inaccessible.
Which is what you did in your previous paper.
Yes. But yes, this idea maybe feels slightly more accessible. Somehow you just need to do a random version of when you do the strong separation condition, and then it will falls out.
And then one other question, just this idea of using the spectral gap from distance transfer operator to get Fourier decay, it seems like a very nice idea. Do you know about the history of like where this was first? The intuition right here.
So I think maybe using the spectral gap explicitly, maybe this is Sahlsten and Stevens, but somehow it's about this driving force for non-concentration, and somehow this proposition here is this non-concentration proposition. Somehow you kind of have this non-concentration statement in your work somehow coming from the non-linearity of your function. You have this non-concentration dates back quite a long way, at least to Kaufman. Maybe it appears in these earlier works of Profelic and Romare, and maybe an earlier work of Kaufman as well. Yeah, there's a paper of Jordan and Sahlsten as well, which is relevant to this connection.
Maybe one question. Maybe I zoned out this, but exactly for this twist operator, how do we know exactly that will be a spectral gap there?
So
for large omega, or for every omega, just you have better control for large.
yes, so this is highly contributed. This is exactly what the non-conjugacy condition gives you. So remember the first part of the talk I was saying, okay, you're non-conjugate, and then this gives you your unique condition, which somehow tells you that you have two words for which this difference of the log of the first derivatives is very well behaved.
Ah, I see. So this,
And this, you take this condition and you can. Okay, so what did I do? I said I want to get to bound the infinity norm spectral gap. I said, okay, well, in fact, you don't need to look at this. You need to look at the L2 norm of some suitable integral. And when I look at my integral, I can say, okay, well, do I get cancellation with all these different complex numbers? And the point was the unique condition guarantees cancellation, because or at least it guarantees on any small scale, you're going to get a little nugget from which you have cancellation. And the point is these the sum of the contribution from all these nuggets, and this gives you a spectral gap. The technical obstacle you have to overcome in the presence of overlaps is it's possible that these nuggets have negligible measure relative to the set it lives within. Right, because of the failure of the doubling property. And that's why you have to do this random stuff.
So do I understand correctly that basically the whole thing can maybe with some extra further difficult technicalities go through to Gibbs measures?
Yes. So absolutely. So and yes, we prove this. So Anna mentioned this work with Osama and Tuomas. So we through a higher dimensional version of this Gibbs measures with the strong separation condition in one dimension. This was this paper of Sahlsten and Stevens. And yes, it entirely goes through. The one place it all breaks down is we don't have this nice disintegration of the measure, this disintegration of the transfer operator for arbitrary Gibbs measures.
No.
In the overlapping situation, we don't have this because
You really need to go out from symbols.
yes, but yeah, just we really need the potential to be a constant function in this case. If you have a non-constant potential, then yeah, you have this dependency on x, and then it just breaks down.
Sorry, just to probably on that, but you don't get the overlapping result in higher dimension even for just self-performed measures, right? So it's not just the Gibbs measure thing that's causing overlap with the overlapping measure.
Sorry. Yes, you're right. In higher dimensions, you don't have this. This is a real good obstacle by. Okay, so maybe you can get quite as clean a result as non-conjugate gives you polynomial Fourier decay, even in the presence of overlaps. But you absolutely, with the existing arguments of Osama and Tuomas and this disintegration approach and the paper of myself and Tuomas, you could absolutely yes, you could absolutely prove something in this direction. You could prove an overlapping self-conformal or something same in arbitrary dimensions, but maybe not the ideal one. Maybe if I don't know if I chose my favorite I don't know, K copies of my favorite IFS in higher dimensions, chosen so they overlapped, disintegrated in this very deliberate way, it would all work out perfectly. But just doing the disintegration for an arbitrary IFS in higher dimensions, I think the argument certainly is slightly more complicated than in lower dimensions. And the unique condition is also slightly more demanding too.
All right. Thanks, Simon, again.